This chapter is in continuation with the last chapter, that was interference. So the last chapter, interference, and this chapter both are part of what we call as wave optics, wherein we study the wave nature of light. Okay, when we say light, then it is not only the visible part of light, but it is the whole electromagnetic spectrum. So whatever we are studying is applicable for all the EM waves. Okay, but generally we say light because light is the most tangible part of that spectrum. So whenever I'm saying light, so actually I'm referring to the whole spectrum. Okay, you have to keep this thing in mind, whether it is ray optics or this. Okay, so when we say light, so light of all sorts, like electromagnetic waves of all sorts. Diffraction and polarization we are going to study in this chapter. In the simplest possible manner, how do we define diffraction? Forget about physics and all that. Okay. Think of it like this. Suppose you are in your home, there are several rooms. In one of the rooms, two people are talking. In a room, in your house, two people are talking, and you are outside the room. You are outside the room, and the door of the room in which both persons are talking, the door is open, but you are not directly in front of them. You are not in front of them. You are away from the door. Okay. You are away from the door. You are not directly facing them. Okay. Still, you are able to hear the sound. Okay, so when the person talks, the sound waves propagate, and when the sound wave reach the window or the door, then at the opening, it bends, it spreads, and that's how I am able to hear, even if I am not directly in front of the person who is talking. Okay, this bending of wave is known as diffraction. It happens with all the waves, light, including light. Okay, and this was the biggest proof that light is a wave. You see, in the last lecture we discussed that how over thousands of years the controversy continued whether the light is a wave or a particle and all that. Okay, but this diffraction further provides a solid proof that light actually indeed is a wave. It diffracts like any other wave, like sound wave. Light also diffracts. Okay. Let's understand diffraction by one other in case of light. Okay, with regard to light, we have very simple, beautiful experiment which will help us to fully understand the meaning of diffraction. First, let me write down diffraction. Okay, what is diffraction? Diffraction, okay. It is bending of wave bending of wave from the boundaries, boundaries of obstacles, holes, okay, holes, apertures, etc. Okay, this is a very general statement. Okay, so I have this obstacle. I kept this obstacle in path of light. The light beam is coming in this direction. Now it encounters this obstacle. Now from the boundary, light is going to spread. Light is going to bend. Okay, so this bending or spreading, okay, of wave from the boundaries of obstacles, holes, apertures, etc. This is known as diffraction in the most simplest, non-technical term for a layman language. Okay. Now let's try to understand it through a simple example, very simple example. Okay. Now it's like this. Imagine that there is a dark room. a dark room. Okay. I have this room. I have this room here. Okay. It is closed from all sides. No light can enter. Not a single ray. No light can enter. You are inside this room. You are inside this room here. What will you see? What will you see? Nothing. Okay. It will be complete, pitch black dark. Okay. Now, let's say that there is one opening, a very small window, a small opening. Okay. This is a small opening. Okay. Just for simplicity, let's say that I have this small opening here, a circular opening. This is a circular opening. Okay. Now, from outside, parallel beam of light is incident. Parallel beam, absolutely parallel, which is incident normally on this wall. This wall has a hole, aperture. I am inside the room. The room was otherwise completely dark. What do I expect? What do I hope to find on this other wall? The opposite wall. What I expect will be a bright spot. What I expect, I know that light travels in a straight line. Light travels in a straight line. Okay. I have this knowledge. From that knowledge, I expect a bright spot of exactly same size. Okay. This is expected. This is expected. What I expect. But what I actually find, is a bright spot of larger area. Okay. This is the actual observation. This was expected and this was actual. And not only that, not only this, around this bright spot, I see fringe pattern. Okay, this is the fringe pattern. Fringe pattern. This is very interesting. Unexpected, absolutely unexpected. Okay. The bright spot extends up to this point. That means the light. It is possible only if the light is bending from this point here. Otherwise, it's absolutely impossible. How can light reach here? That means at this point the bending has happened. Spreading has happened. Not only that, I find fringe pattern also. So this whole phenomenon, this bending plus this formation of fringe patterns, this is known as diffraction. Now if the light is a particle, this is absolutely impossible. Okay? If I throw the particles in this direction, I can expect particles only to be in this region, this dotted region, the expected region. It does not happen. It's a wave. Light is absolutely a wave. Okay? So this is one simple experiment. Let's look at one more. Okay. I have this wall, this is screen. Okay, and light is incident from this side. Entire wall will be illuminated. Okay, I've made this arrangement that only the parallel light is available. I allow only the parallel light. I've made this arrangement. Okay. Now, I can use a convex lens to achieve this, or any optical arrangement. Okay, such that I get a parallel beam of light. I have a screen here. What do I expect? And what do I find? I find that this whole screen is illuminated. It's bright. The whole screen. Okay. Now, if I keep an opaque object here, opaque, let's say it's an opaque disc. Okay. opaque disk. So I have this wall here, light is coming from this direction. In front of the wall, I am keeping this opaque thing. What do I expect? I expect a shadow. A shadow on this wall, on this screen. So a shadow of what size? A shadow of what size? Same size, exactly as this. So this is my expected result. Okay. This is expected. This is what I expect. I should get a shadow. So I will have this dark region here, dark region. Outside will be bright. Expected. Okay, commonsensical. But that does not happen. What actually happens is I get a shadow of smaller size. I get a shadow of smaller size. Okay, this is the shadow. Okay, this is shadow. Okay, dark region of smaller size. Smaller size, and not only that, fringe patterns around this. Okay, fringe patterns. Okay, similar to this here. So this whole thing is dark. Okay, this is dark, this whole thing is dark. And now the most astonishing thing, do you know what it is? At the center of this shadow, I get a bright spot. Okay, at here at the center, right here at the center of shadow, I get a bright spot. This is the most amazing thing. How possibly this could happen? This whole thing is known as diffraction. Okay, are you able to develop some idea? Just basic idea of what diffraction is. Most astonishing thing. At the center of this dark spot, I get a bright spot. Well, that is diffraction. Let's try to understand. We can understand it. Okay. Whatever concepts we learned in the last chapter, that was on interference. Okay. We are going to use those concepts directly here. So I am not going to explain too much. Okay. As it is, whatever concepts we studied, everything we are going to use, whatever is required. Okay. So if you have not done that chapter already, which chapter? Interference. Better you do it first. Okay, because now on, I'm directly going to use all those principles that we developed, that we used, okay, understood in the last chapter. All right, okay, understood. Okay, so let's try to see why it happens. Let's try to see why it happens. And you know who is going to explain this? Which concept is going to explain this? Okay. The first concept that we studied in the last chapter, wave fronts and Huygens principle. Wave fronts and Huygens principle. It's like this. Let's say that I have this a wall here. Oh, this is an opaque wall. Okay. This is an opaque wall. Opaque wall with an opening, okay. Also known as, you can also call it hole, aperture or slit, okay, of size A. Size A. What we are going to do is known as single slit diffraction. Single slit diffraction. Okay. Now, this size is A. This size here is equal to A. Okay. Well, it not. I will write it later on. Okay. Let me just keep some space here. So this is my opening here. From here to here, this is the opening. Now on this wall, Okay, in front of this wall, I have a screen here. This is my screen on which I am going to observe the diffraction pattern. On this whole thing, a light beam, a parallel light beam is incident normally. Okay. What will be the corresponding wave front? Wave front corresponding to this beam. Set of parallel planes like this. Okay. So as the light propagates, we can think of propagation of light in terms of the propagation of wave front. Wave front. Okay. So at this point here, wave fronts are continuously arriving. Continuously they are arriving. Continuous process. Okay. So at any given point, the wave is propagating in the medium. I observe at one point. If I think in terms of wave fronts, at any given point, the wave fronts are continuously arriving all the time. Okay. So wave fronts are continuously arriving at this aperture. Now the part of wave front which is in front of this opaque wall, it gets reflected. But this is not opaque. Here I have an opening, aperture, hole. Okay. Every point of the wave front, Huygens principle, what it says, every point of the wave front is a point source. Okay. So every point here of this wave front, it is actually a point source. How many point sources? How many point sources? Within this aperture, within this opening, how many point sources? Infinite. Infinite point sources. All of those point sources start emitting secondary waves of same frequency, same wavelength, same speed. But this is a plane wavefront. Now they become point sources, the spherical wavefront. They will start emitting waves like this. Infinite sources. Now, and at any point on the screen here, light waves from infinite sources, they arrive and interfere. So light wave from infinite sources arrive and interfere at any given point on the screen, and they interfere and produce a pattern, fringe pattern, that is known as diffraction pattern. Same thing was happening in Young's double slit experiment. The same process. In the last chapter, we called it interference. Exactly same process happening here. We are calling it diffraction. Why? What is the difference between diffraction and interference? What is the difference between diffraction and interference? Answer is absolutely no difference. Both are absolutely same. Fundamentally, basically, both are exactly same. They are same thing. It's just superposition of waves. The only practical difference, and there is some difference in the method of analysis. That's it. Fundamentally, basically, both are same, but the way we analyze becomes different because of the nature of the things that we are handling. In Young's double slit experiment, we were handling just two slits, double slit, two slits, and those two slits were point-like, very small, pinholes. We call them pinholes, very small. So we were assuming them to be 2 points. That's it, 2 points. Here, this is a finite thing, finite aperture, finite slit, some width. This width is given. This width is equal to A. It is given. So here I have infinite sources. Okay. So if the number of sources is small, maybe 2, 3, we call it interference. When it is large, hundreds, thousands, infinite, then we call it diffraction. But see, diffraction also interference is happening. Only thing is the number of sources have increased dramatically from 2 to infinite. This is diffraction. We call it diffraction. Okay, you got the point. Okay, we struggled so much handling double slit in the last lecture. How do we hope to handle this infinite sources? Do you think you can handle it? Can you think? Can you even imagine? We can handle the infinite sources. I have infinite sources. Okay. The thing is, no, we cannot. First thing, but with some good logic and some symmetry arguments and some good logic, we are going to handle it, and we are going to actually derive the fringe pattern, the location of bright fringes and dark fringes, the same way that we did in double slit experiment, using some logic, some very excellent, beautiful logic. Okay, let's see. What I want to find, first of all, your object should be clear. What I want to find, I know that they are going to produce interference pattern. I can call it fringe pattern. Generally, it is called as diffraction pattern. I want to find where are the maximas, where is the bright fringe, where is the dark fringe. That's what I want to find. Okay, that's what is our object. To find the location, locate the bright fringes, locate the dark fringes, where they are. Okay, this distance, let's give it some name here. Let's say it is equal to capital D. The only change is in case of X double slit, the difference between slits was small d. Here I am taking it as A. This is the aperture, the size of aperture. Size is A. Wavelength is lambda. Okay, let's see how to handle this. Let's see how to handle. How to handle. Okay, it's like this. I'm drawing this figure here. Okay, so this is my aperture here. This is the middle point of aperture. Okay, this is the middle point. Let's say it is O. Okay, this is the middle point, and in front of this middle point, I have what we call as center of the screen. This is the center of the screen. Okay, let me call it C. C here. This distance is capital D. Capital D. Let's look at some point, a general point. Let's say that this point is P. At point P, I want to find how the interference is happening and whether it is going to be a bright fringe, dark fringe. What should be the conditions to get a bright fringe and dark fringe at this point. This angle is theta, the angular position. Now, light is incident in this direction. Okay. Wavelength is lambda. How many sources I am going to have? How many sources? I am going to have infinite. Okay, infinite sources. Okay, infinite sources here. Okay, and see this beautiful thing. Divide slit in two halves. Both halves will have infinite point sources. Makes sense? I divide infinite into two halves. Both halves are going to be infinite. Okay, both halves are going to be infinite. So I divide slit in two halves. Both halves are going to be infinite. Now look at pair. Okay, look at pair of waves. Okay, one from look at okay, not look at, okay, consider. Why look at? Consider pair of sources. Consider pair of sources, okay, separated by A by 2. Consider pair of sources one from each half, separated by A by 2. Okay. What it means is that it is this. You consider one wave here, okay, and one wave here, this. Okay. What is the distance between these two? Distance between these two is a by 2. A by 2. And consider one wave here. Pair of points. Pair, okay? So let's look at this pair here, not this one. Let's look at one pair here. So I'm dividing this whole thing in two halves. Both halves are going to have infinite point sources. I'm considering one point source from one half, the other from the other half. Distance between them is a by 2. Okay? If B is very large as compared to A, then path difference between waves in the pair is equal to d sin theta. Okay, here also there will be infinite such pairs. Try to follow the logic. Two halves, each half going to have infinite sources. I am making pair of waves. One wave from upper half, one from the lower half. Separated by a by 2. How many pairs I am going to have? I am going to have infinite pairs. I am going to have infinite such pairs. Now, if this condition is satisfied, D is very large, then path difference between waves in the pair. What will be path difference? The path difference here, okay? This is the path difference, and this will be equal to d sin theta. A sin theta, not d sin theta, is equal to a by 2 sin theta. Understood this? Understand? You understand this? This is the result we are using directly from the previous chapter. I am not going to explain, okay? I said it in the beginning. You have to be comfortable with that chapter before doing this. Do not blame me. Okay? So this distance is a by 2. So this path difference here is going to be a by 2 sin theta. Now, if I look at any other pair, this is one other pair. Here also, two waves of the pair are separated by same distance. Okay, so here. So this is 1 and this is 1 dash, this is 2 and 2 dash. If path difference between the waves of one pair is a by 2 sin theta, then path difference between waves of all the pairs, all the infinite pairs, will be a by 2 sin theta. This is the crux. This is the crux of this logic. If path difference between the waves of one pair is a by 2 sin theta, then path difference between the waves of all those infinite pairs will be a by 2 sin theta. And now, if the waves of one pair interfere destructively, if the waves of one pair, note it down, if the waves of one pair interfere destructively, then waves of all the infinite pairs will interfere destructively. Okay? What will be the net result? Net result will be destructive interference, a dark fringe. Okay? Do you understand this? Understand this? This is the path difference between waves of one such pair. All such pairs are going to have same path difference between the waves in that pair, infinite pair. If one such pair is interfering destructively, then all the pairs will interfere destructively. Okay? Then overall, I am going to have destructive interference, I am going to have minimum. Okay? To get minima, this delta x should be equal to, it should be lambda by 2, 3 lambda by 2, okay, 5 lambda by 2, okay, etc. This becomes a by 2 sin theta is equal to lambda by 2, 3 lambda by 2 and 5 lambda by 2, all that. So A sin theta, it becomes lambda, 3 lambda and 5 lambda to get minimum. Okay, all right, makes sense? Does this make sense? Now the next part of this logic, divide slit in four equal parts. 4 equal parts. Okay, all parts will have infinite point sources. Consider pair of sources, one from each part, okay, separated by a by 4, okay. There will be infinite such pairs, exactly same thing. Then path difference between waves in the pair. Now what will path difference? Now I am dividing it into 4 parts, okay. Then this will become a by 4. This will be equal to a by 4. Okay. So what will be condition for the next minima? Okay, it will be like this: a by 4 sin theta is going to be lambda by 2, 3 lambda by 2, okay, 5 lambda by 2 and all that. Okay, what will be a sin theta? A sin theta will be equal to 2 lambda, 6 lambda, 10 lambda and all that. Okay, so in 4 equal parts, then make it 6 equal parts, and exactly same logic continues. Exactly same logic in 6 equal parts. Then what do I get? I get a over 6 sin theta is lambda over 2, 3 lambda over 2, 5 lambda over 2 and all that. Okay, what is a sin theta? It is 3 lambda. Okay, 3 lambda and then 9 lambda and then 15 lambda and all that. Continue doing this. 2, 4, 6, 8, 10, 12. Continue doing this, then what will be the general condition? Okay, general condition for minima. General condition for minima. Okay, it will be a sin theta is equal to n lambda. This is the general condition. Okay, this will be equal to lambda, 2 lambda, 3 lambda, okay, like this. Okay, understood? What are these? These are minima, dark fringes. Okay, so I am going to write this here. I'm going to write it here, okay? So I have this aperture. This is my aperture. Okay. This is theta. This is size A. This size is A. This light is lambda. Okay, so what will be sin theta? Sin theta is equal to n times lambda over A. It will be lambda over A. Okay, on both sides. Okay, do you understand this? When we are talking about path difference, we are taking the modulus of that. Okay, so it will be on either side, not on one side only, on either side. It will be on either side. Okay, lambda by A. This is 2 lambda over A, this is 3 lambda over A. Okay, so I am going to get a dark fringe here. This is dark fringe 1, first dark fringe. Here, this is dark fringe 1. What is this angle? This angle is sin theta. Okay, so here sin theta is lambda over A. Here also sin theta is lambda over A. Okay, Now I will get another dark fringe here. Okay, this is another dark fringe. Okay, let me say it is here. I have to draw a few more information here. Okay, this is another dark fringe. This is D2. This here is D2. Okay, this here sin theta is 2 lambda over A. Okay, and here sin theta, here also sin theta is 2 lambda over A. Okay, this is second dark fringe. What are these? Positions of dark fringes. Now, between two dark fringes, we get a bright fringe. We get a bright fringe. Okay, so here between two dark fringes, I get this bright fringe. I am calling it V1. Okay, this will be central max. What will be sin theta here? Sin theta will be 0. Okay, so sin theta is going to be equal to 0, 0, and then here this is also bright fringe, okay, this is sin theta, it will be between these two, okay, it is 3 lambda over 2a, and here also between two dark fringes I get a bright fringe. This is a bright fringe here, here sin theta is 3 lambda over 2a, it's like this. Okay, so 0, this will be 3 lambda over 2a, then 5 lambda over 2a, and all this. These are positions of bright fringes. Now this is known as central maxima. This is known as central maxima. Central maxima, okay? Central maxima. Now, intensity variation. Intensity variation is something that we are not going to discuss here. Okay. I will just plot the graph and you have to remember that graph. That's it. Okay. This is all the others. The first one here, it corresponds to central maxima. This is central maxima. Okay. All the others are known as secondary maxima. Secondary maxima. All the others. This one is central. This one is central. Okay. The other one, all the others will be secondary maxima. Secondary maxima. Now look at the intensity variation. Okay, this is very important. Here intensity is 0. Here also intensity is 0. It is dark fringe here, dark fringe here. Okay. In between, intensity changes like this. Very interesting graph. That's how intensity changes. Okay? And then drastically it reduces. Intensity of central maxima is maximum, and the intensity of secondary maxima, they drastically reduce. Drastically, okay? I will write down the values, you will understand what is the meaning of drastic change here. Okay, that's how drastically it reduces. Okay, this is D3. Here also I am going to get a bright fringe here. This is D3. In between I am going to get a bright fringe. Okay, you understand? Now, if the intensity here is I max. Let's say that intensity of the central bright fringe is I max. Okay. Then here intensity becomes approximately 0.05 I max. It reduces 95%. Drastic reduction. But still there is intensity. Okay. More important than drastic reduction is the fact that there is intensity. That is more important. Okay. It is not 0. So outside this region also the light reaches. Okay. This intensity here is approximately 0.016 I max. I max. Okay. This is central maximum. Okay. This thing here, this thing is central maxima. Central maxima. All the others are secondary maxima. Remember this. I'm going to clean all this, okay, so that it does not look crowded. Okay, it should not look crowded. And I hope that you are able to see it. Okay. All right. Now, all the others are secondary maxima. This is here. Here, this is, okay, this is first, this point here. Okay, you see, this is secondary maxima. This is a central maxima. Central maxima. This point is first, secondary maxima. Okay. Here, this will be second. Okay. Second, secondary maxima. Okay. Similarly, here also, this becomes first, secondary maxima, and here this thing here becomes second, secondary maxima. Okay. Now, what will be angular width? Angular width of central maxima. Angular width of central maxima. Okay, is equal to 2 theta. 2 theta. Now, if D is very large, very large, D is very large, okay, then this will be approximately equal to 2 sine theta. Okay, if theta is small, if theta is small, if A is small, you see, if lambda is small, this lambda is a very small value for light wave. Okay, if aperture is also this whole ratio is small, then okay, let's say that sine theta is small, then theta will be approximately equal to sine theta. Now this is going to be equal to 2 times of lambda over A. Lambda over A. Okay, you understand this? Now if this D is very large, if this D is very large, okay, as compared to A, what is D? It is the distance here. Okay, it is this distance here, very large. Okay, in that case, linear width of central maxima okay, or let's say that no, I think let me not put this condition here. Let me not put it. This is angular width. Okay, what will be linear width? Okay, this distance is from here to here. Okay, it will be equal to, this is D. This angle is theta. Let's say it is theta for the first minima. I want to find the whole thing from here to here. Let's say this is y. This also will be y. So linear width of central maxima is equal to 2y. It is equal to 2y. Okay. If theta is small, then sine theta approximately equal to tan theta. Okay. Now, so this linear width will be equal to tan theta, and tan theta is y over d. Does that make sense? This is y, this whole thing is d. So if theta is small, and that will happen if this aperture is small. If the aperture is small, theta is also going to be small. Okay, it is small, then sine theta is approximately equal to tan theta. What is tan theta? Y over d, and that's it. Okay, that means y is equal to d sine theta. Okay, so this is going to be equal to 2 times of d into sine theta is lambda over a. Lambda over. That's it. What it is? It is the linear width, And you have to remember this formula. You actually have to remember this. D times 2D times lambda over A. Okay. Okay, do you understand this? Under what condition? Under what condition? When theta is small. Both. When theta is small. Okay, that is lambda over A is small. Okay, so angular width and linear width. Okay, makes sense? Makes sense now. Okay, noted? Okay, now next one last thing, then we will do problems. If D is very large, okay, if D is very large as compared to A, then interfering waves are almost parallel. Okay, this is called Fraunhofer diffraction. Okay, and in other case, it is called Fresnel diffraction. Okay, the conditions that we derived are conditions for what type of diffraction? Fraunhofer or Fresnel? Okay, they are for Fraunhofer diffraction. Fraunhofer. Okay. In our syllabus, we have to study only Fraunhofer. Fresnel becomes quite mathematically challenging. Okay, so it is not part of this course. We study Fresnel diffraction in advanced courses of wave optics. Okay, not in this course. We are not going to do this even in our advanced course. Okay, so we have to study only the Fraunhofer. So whatever we are studying is Fraunhofer. Whatever questions will be asked, by default, you have to assume that it is Fraunhofer. Okay, you never think about Fresnel. Just the name is enough. That's it. That's what you know. Just the name. You just know the name. That's it. Okay. What is the other case? The other case is that this is at finite distance, not infinite, but finite distance. Okay. Then that will be Fresnel. And that analyzing becomes very difficult, challenging. Okay, we are not going to do that. Okay, let's do some problem. Okay. Okay. Let's do it. Question. Light of wavelength falls, light of wavelength 600 nanometer falls on a slit 1 mm wide, and diffraction pattern is observed on a screen 2 meter away. Okay, we are going to do direct problems based on this. If you know this diagram, you know everything. All the problems we are going to solve based on this Fraunhofer diffraction. Okay, 1 mm wide slit and diffraction pattern is observed on a screen 2 meter away. Okay, what is width of central maximum? Direct problem. Central maximum. Okay, do it. I hope that you should be able to do it comfortably. Okay, without much difficulty. Okay. In a diffraction pattern of a slit of width A, single slit, we are doing single slit diffraction, slit of width A, okay. First minima is observed at 30 degree. Okay, what is angular position of first second minima, okay, second minima, and then first secondary maximum. Okay, secondary minima, second minima, and first secondary maximum. Let's solve it. Let's solve both. Okay, this is width of size A, size of aperture. This is the angular width. Of central maximum. If the screen is 2 meter away, okay, slit size is 1 mm, wavelength is 600 nanometer. Okay, what is width of central maximum? So this whole width I have to find out. This linear width. What is this linear width from here to here? Okay, we just derived it. Angular width is equal to 2 theta naught, let's say, okay, 2 times of lambda over A. Linear width is equal to 2 times of lambda over A times D. Okay, this will be 2y here, so y will be equal to d tan theta. Tan theta will be equal to sin theta, and that's how we can find it. Okay, angular width, this is linear width, which is d times of this. Now, so we have this answer, 2 times of 600 and 10 power minus 9 nanometer over A, 1 mm, 1 10 minus 6 times D. D is 2 meter. We have this answer, 2 and 2, 4 and 6, 24 into 10 power, this becomes minus 7. 6 into 12 and 24, minus 7, minus 1. Okay, this is 2.4 meter. No, this is minus 3 millimeter. Okay, it's minus 7, minus 4. So 2.4 and 10 minus 3 meter, it will be 2.4 millimeter. Now what it means is that I have this opening, I have this hole of size 1 millimeter, and on the screen here I see a bright spot. Bright spot of what size? 2.4 millimeter. With the first experiment that we discussed. Okay, this slit size, opening size is 1 mm. This size of central maxima is 2.4 mm. The light is spreading. Okay, this is diffraction. Plus we are getting this diffraction pattern also. Okay, now second one. In a diffraction pattern of a slit of, you see, now this angle is not small. The angle is not small. Okay, so we cannot use approximation. Now what it says, okay, is this. In a diffraction pattern of a slit of width A, first minima is observed at 30 degree. Okay, 30 degree. That means this position here. This is first minima. Okay, that means sine first minima, okay, sin theta is lambda over a. Okay, that means lambda over a is equal to sin 30 is equal to half. Okay, now what I have to find? Second minima. What will be second minima? Second minima. Okay, for second minima, what should be sin theta? It should be equal to 2 times of lambda over a. Okay, first minima is observed at 30 degree. So this is 30 degree here. So I got lambda over a. Second will be 2 times of lambda over a. 2 times of lambda over a. That means where it is. That means 1. Okay, so theta is 90 degree. That means it is never observed. The second minima is never observed. Okay. Now first maximum, first secondary maximum. This is central maximum. After this, all the others are secondary maxima. Secondary maxima. This becomes first secondary. This becomes second secondary. So first secondary, it will be between d1 and d2. So sin theta 3 lambda over 2a. Okay, this will be sin theta is 3 lambda over 2a. Okay, so 3 over 2 and half. This is 3 over 4. That's it. This will be angular position of the which one? First secondary maximum. Okay. Okay. Okay, let's do few more problems. Few more questions. In a diffraction, in a single slit diffraction pattern, okay, with light, okay, in a single slit diffraction pattern, okay, with light of mixed wavelength 6000 angstrom and lambda. Okay, with light of mixed wavelength. So I have two wavelengths, 6000 and some unknown and lambda. Okay. Now it is observed in a diffraction pattern of this. Okay, first minima of 6000 angstrom, okay, coincides with first secondary maxima of unknown wavelength lambda. Okay, find lambda. Okay, should be easy to solve. It should not be difficult. In a single slit diffraction pattern with light of mixed wavelength 6000 angstrom and lambda is given, everything is given. First minima of 6000 angstrom coincides with first secondary maxima of unknown wavelength. First secondary maxima. This is the first secondary maxima. This is the first minima. Okay. That means first minima of this. First minima of this will be equal to 3. Okay. First minima of 6000 is equal to first secondary maxima of lambda. Okay, both coincide. That means sin theta is going to be same. Okay, so lambda over a. Okay, so this is 6000 over a is going to be equal to 3 lambda over 2a. So that's it. That's how simply we do it. Okay. So I get lambda 4000 extra. 4000 extra. Okay. Next class we are going to do a few more problems. Okay. We will continue this. We have to do a few more problems. We have to study about resolution also. Resolution of eyes, resolution of a telescope. Okay. We will do it in the next lecture.